Hi, today I'm going to talk about a significant part of the project, which is data harvesting from studies. Harvesting from studies basically drives the system, which means it needs to be done and accurate. Microbiome prescription has harvested itself. However, how it's harvested, some people disagree with parts of it. Many people disagree with different parts of it. Um, and some of the reasons are connected to a bunch of decisions that are made, which I will recap as go through. For a company to own the database of harvested data, they need to do it themselves. So I'm going to describe how to go about doing it, and then it's up to you to implement it in order for the database being produced to become your company's property. So basically, first of all, we're going to start with search strategies. Then we're going to go on and look at the issue of download and convert to text. Convert to text is what I think would be the easiest solution. Everything here is what I think would be the easiest solution. It may not be. You may have a better idea, which is fine. Then we parse text into sentences. Then we identify components, bacteria, conditions, modifier. And the last thing is we convert that into a logical statement, a database record, a prologue statement, etc., showing what we have managed to do. If you're working in Prolog, then you basically just feed all the Prolog statements into Prolog, and it will sort things out for yourself automatically, or generally within some limitations. If a database, then you can do database query languages to look at the data and come to conclusions. So let's go on and look at the bit by bit steps. First of all, for search strategy, we want as a beginning to list all of the bacteria's first name. Why? Because we are bacteria oriented. Now, we could say we want all bacteria names such as Lactobacillus reuteri, but the catch is generally the compound names all have a first name. And if we isolate just the first name, we will capture everybody who has that as a first or second or third names. Just simply a way to simplify things. Also, it means instead of going through um, 18,000 names to search for, you only have probably 5 to 8,000 names, a great reduction. And then next step is, once you get the name, all the bacteria names, and where do you get them? Well, we'll touch on that shortly, but basically, because we are trying to use the NCBI taxon numbers, we want to get the names from the NCBI site, and it's available as a variety of FTP files and download, and the files do give some of the alternative names, but as you will discover going through more recent studies, there are other name conventions out there which are not necessarily in there. Some cases it's because somebody put G underscore lactobacillus as the name, and the G underscore variation is in there. Other cases is lactobacillus underscore reuteri, or other variations, square brackets around it. So there's a dozen different ways that papers are published with the names, which will be a endless challenge because you see somebody will habitually come up with a newer way of doing it. So we want to now identify the sources. My usual source, which is used for microbiome prescription, was the U.S. National Library of Medicine. There are other sources. The PubMed is used because it's a totally free site. The other ones generally require subscriptions. And if you take a look at my Enterprise Architect notes, you will find some of them listed. I think I list a half a dozen other alternative sources. And you will find lots of things. Just ask Perplexity for a list of sources, and you will get a list of different sources. So identify the sources, and now you want to write code to automatically search the sources for each one of these bacteria names. So quick pass, let's say we have 8,000 bacteria names, including historical names, which sometimes the older studies will use, and even some modern studies will still use the older name, depending on where people are in the world and how current they are. And we want to search each source for each one of those names and then get a complete list of every paper on that source that mentions that name somewhere in the document. Some cases you will have the joys that the name is mentioned, but it's actually a person's name because the bacteria was named after a person. For example, E. coli Nissle, Nisse. Nissle is a early researcher's name. So you're going to get papers by the person and the um, studies dealing with this particular thing. So there is a lot of collision in naming. And it's one of your greatest challenges is trying to resolve the naming. And so want to build logic to get differences from the last research only. You don't want to have to go and look at all of them. PubMed, so the microbiome prescription search basically keeps track of everything up to whatever the last PubMed ID, PMID is. And then next time it asks for anything with this particular name after that particular ID, which means the only thing I get is differences, which means my processing time is relatively short. So make sure you look at building logic to get differences only from the last search and get that in early because it will save you having to sort things out, and especially if there are ways of putting time frames on. PubMed studies can't apply dates to it, and that's to make use of the publish on PubMed date, which gives it, but I generally find the PMID is just as good because it is a monotonic increasing sequence number. So let's go on. So what you want to do is download and convert them to text. Now that you prior have gotten a link or a address to find every single one, wherever they are, you want to download and to convert it to text because we need to convert the text. We need to convert the full text of the article into individual sentences. The document may contain spreadsheets as appendices or data sets or diagrams that may need to be flagged for manual review later. And I point out diagrams because often data shows in a diagram which is significant or which can be extracted, but they just didn't bother writing out the full text for it. They just said, okay, yeah, as shown in diagram 4. And you have the shifts of bacteria which are high and bacteria low in diagram 4, and there are a total of 65 listed there, but I only mentioned a few examples in the actual text. So diagrams, spreadsheets, which can be rich in data, and data sets should be flagged for manual review later. For the moment, for the first cut through, you don't do it. Later on, you want to go back and be able to pull up all these items and manually inspect them when time and resources permit. You want to save each document with an integer identifier, which will be your own identifier. Often the papers have identifiers to them. You got PMCID and PMID, depending on if you're looking at a summary or the full text for PubMed. So you want to have your own identifier, and then you want to have the other identifier could be the DOI identifier, but you need to have your own one. And often you want to have your database table showing maps between the two of them. For example, something may have a DOI ID and a PMC ID. You want to identify the two of them match. Fortunately, PubMed will generally give you the DOI ID if it's available, so you can just store both of them. But later on, when you pull in DOI, find different source of studies and pulling them in with a DOI ID. You want to make sure whether or not you have already processed it, taking it from the U.S. National Library full text archive. So you need to keep track of multiple identifiers for articles, and the more identifiers you find, the more to be added, and you want to keep them all in sync so that you don't spend time double entering data or double processing data. If the text is not in English, for example, you will find some in Russian and some in French and some in Spanish. You probably want to make use of the translation API to convert all the text to English for processing, simply to save the hassle. Whether or not the translation is accurate is another question, but generally the translations are reasonably good, so you can just go ahead and proceed with the text version there. So you do search, find, download, convert to text. Here is a simple example. Using the National Library of Medicine, the PMC, I type in Reteri, I get 17,000 studies in which the term Reteri is mentioned. And as you can see down on the bottom of the first article, I can have a link to the article, which is in HTML, which is real easy to grab and download. And all you have to do is strip off the headers and footers as appropriate. And you also have a PDF version, which you have to download. Or you could download as an alternative and then parse the PDF. Some cases you will find only the PDF version is available. Other cases you find both. And in some cases you will find that the article is only available as a scanned version of the original article, in which case then you need to master the art of applying OCR to a PDF to get the text file produced. Remember, the main output up at this point in view is a text file containing the whole article. So let's go on. Next thing is parsing text into sentences. And we want to give every sentence, and generally sentences are identified by a period. However, be aware that a period can also indicate the decimal point. So you need to make sure whichever parsable tool you're using identifies and tells the difference between a period and a decimal point. And you may, in some cases, want to do a pre-processing to identify, to separate decimal points from periods by, for example, giving a special ANSI code, which looks like a decimal point, but will be detected as different by your parser. There are a lot of text parsers out there, and which one will work best for medical literature is unclear at the moment, so you may end up having to sit down and use every single one to find out how well they parse and how usable the output of the parse is. So you got some work there, you got some exploration to do, because medical literature is a language to itself. Each should be tried and then rank order or multiple studies to determine which one seems to do the best job. Some cases you may actually end up wanting to run an article through 2 or 3 of them and process each one of them separately, which is fine. Remember, we are dealing with computerized processing, so doing 3 different parsers is not a particular problem. It's just having to write the code to do it 3 times. And since you should have already written the code for each one of them in your evaluation, it should be a pretty straightforward process, and it will improve the accuracy of your thing. And more importantly, now you have 3 or 4 versions of it, and you can see whether or not there are disagreements with the parsing and the interpretation, which allows you to improve the quality. So you got a bunch of tools to explore making use of, and you got a whole bunch of articles. How many should you do? I would say a minimum of 100 articles. 1,000 would be much better, but you need at least 100 articles to find out how good the study is, parsing is going to be. So next stage is you have a parsing sentence, and when you're parsing the sentence, you should give each sentence a number so the antecedent can be identified. If in sentence 65, it makes reference to something earlier, and it says the word it or other antecedent, or the previous studies, you need to go back and sort it out. And since the antecedent, you know it would be at a lower sentence number. So hence you want to have a number. Also, when you parse it apart, the parsing apart for each one of the possible tools should end up with the same sentence number. If they're not a different agreement on sentence number, then you may want to do some exploration as to why there's a difference. Often that will catch dumb, silly assumptions in your processing, which should be fixed. So now that we have sentence parse apart, we need to identify components. Although we have things like noun, verb, subject, object, adverb, adjectives, and other parts and qualifying phrases, the key components we are looking for are bacteria, conditions, and modifiers. The rest of the parsing the sentences apart, it will deal with a bit later down. So we have bacteria name. Since we are using NCBI taxon numbers, or suggested we use it because it gives a clear, simple integer value, which makes it easy for data processing. The several files we're going to download there. The one file is the taxon name with the standardized name with the hierarchy. There's another one, nothing but alternative names. Taxon number, alternative name 1, alternative name 2, alternative name 3, 4, 5. Just be aware that about all the alternative names will be found in the literature. Some of them are things like G underscore or square brackets around it, or a underscore between each part of a name, or other ways of hashing things like L dot retere in one page, or LAB space retere is another name. So you end up having to dynamically keep adding funky naming conventions to the database. So, but once you have them reasonably good, you go through, and when you find something that doesn't fit, you just inspect and add it. So it ends up having to do manual tuning regardless. No way around it. Believe me, I wish there was. If a noun is not identified in any of the three dictionaries, the bacteria, the conditions, and the modifiers, then we'll try to find one or more by looking at Grammarly lookup in case it finds it, perfect it. Language Tool Junior Software, if they fail, perhaps regex or taxonomical distance tools may be used, as in, for example, one I've frequently come across that one letter is omitted from a name, in which case it's if you taxonomy or naming distance tool, then you quickly identify it. Oh, wait a minute, you have 99% match or 90% match of this term with this existing term, and therefore you use the name it matches to, and whether or not you correct the spelling in the document or put it in with square bracket, putting a sec and after it, so that somebody later coming in will know it. I would suggest you end up using classic English notation. That is, if you find a word misspelled, insert into text square bracket SIC or whatever one you do, and the spelling you are actually going to make use so that it can be easily reviewed. Okay, so bacteria name is there. Conditions, we want to enumerate all the conditions in scope. It could be everything. It could be all the ICD code, which is fine, legitimate. It could be only a handful of conditions. From those names, we want to use API and ask various APIs what alternative names use for every condition. What it does do, it makes searching the web much easier, and you want to ask exhaustively. And if you ask for one name like irritable bowel syndrome or IBS, and it comes back with 5 names, now you want to do the same thing, ask for each one of those 5 names, what are alternative names. So you want to do it recursively, not just one time and you're done. You want to ask it, and you want to make sure you have exhaustive lists. Now, once you finish doing all the APIs, then you go to the problem of alternative names colliding to multiple conditions. And now you end up having to figure out priorities for which one is supposed to be a matchup. Some cases, it can be resolved by looking at the full text of the article and see if any of the alternative names are listed, and if that resolves it to which one. So you may have several passages of the article to determine exactly what they are talking about. Has occasionally said, oh, wait a minute, no, that's not it. They're using the same initials for something else than what I assumed they were talking about. So you do have a bit of fun there. Again, API calls to find alternative names. Repeat that for each alternative name comes back. Then resolve, identify which ones have multiple conditions. And then you may have to implement code to examine the whole article to try to identify which one of these alternative names match to which one of the original names. Then you also need to ask the AI for abbreviated names for each condition. Oh boy, like irritable bowel syndrome, IBS, irritable bowel disease, IBD, but you occasionally will find some of the abbreviations are used for multiple conditions. Again, we may have collisions, and we need to be aware of them and make sure we identify the correct one by examining the whole article in context. We also may want to use API to ask various APIs what ICD codes are used for each, and then use the ICD to get alternative names. So we have a whole bunch of data mining to find out the whole panacea of names that people have called something. Some cases, you may even bump into ask for historical names, for example, polio and consumption, or tuberculosis and consumption are examples there. If a sentence X uses a name briefly on multiple median parts, the sentence may need to be searched to identify the intent, or even later in the article. Generally, you want to go backwards to see if you can identify it, and then only then do you go forward and look at the full text. So getting your dictionary of alternative names is a good chunk of work there, and like taxonomy is a good chunk of work. You got a ton of alternative names because English is not precise. Unlike mathematics, which is pretty precise. We are dealing with fuzziness in terms of what the terms mean. So you got a bit of work, you got some cursiveness, you need to get familiar with a variety of APIs. Don't work on just one, use several. Again, because everyone is different. Some do a better job than others, and you just want to be exhaustive to make sure you are comprehensive. Modifiers. Ah, joy, modifiers. Enumerate all the modifiers in your initial scope. Use API to ask various API alternative names for each one. Generally, you want to, if possible, find a Latin name, and there may be multiple Latin names for some modifiers. Common names and regional names. Something in England may be called something different than in the US and different than called in Australia or in Hong Kong, especially when we're dealing with, for example, some decorations which are all very popular in China, which has a Cantonese name, a English translation of Cantonese, and a Mandarin name. So you have 1, 2, 3, 4, 5 names or 6 names which are there. In some cases, they are abbreviations also there. So you got a bit of work there. In some cases, you have to actually break things down to the components to identify which one is. As above, we resolve any alternative names assigned to multiple modifiers. So if alternative name is shown up and there's multiple modifiers, you know you need to branch into your processing into identifying which is the likely correct modifiers. Again, ask API for abbreviated names for each modifiers, and again, you may have collisions. We have as above, a abbreviation modifier may have multiple matches. You need to want to look at prior. If a sentence X9, you may want to look back at 1 to 8 to see if you can clarify it. If not, then you go forward and see if the rest of the article identifies. When a phrase suggests a modifier that is not in scope, it should be automatically added to the scope. For example, example, I have cherries in my existing list. I hit cherry tomato. I don't have tomato in my list. Oops, I need to go and add tomato because there is a study dealing with the microbiome shift with tomato, so I have to add tomato to it. But I have a adjective, a word that modifies my noun, which is tomato, which is cherry. So now we end up having to add it as a cherry modifier, as a composite, and we'll come to that in a moment. Okay, so we have the challenge of adjectives and qualifiers. Often with herbs and other foods, like the cherry tomato, we have qualifiers. For example, for honey, you have clover honey, Greek thyme honey. You have a ton of different honeys, and sometimes the honeys have different microbiome modification properties. So we basically should keep them straight so we know what we're talking about. So we end up like with the bacteria having a hierarchy, we may need to have a hierarchy for modifier. For example, honey, clover honey, etc., and we end up having to build up a variety of hierarchy names. We want to be able to ping is exactly like if we find a new type of honey with a adjective which be identified by our sentence parsing software code, then we may have to add that modifier to hierarchy automatically, and subject to manual review is suggested. Similarly, when we deal with conditions, we may need to add in condition modifiers like mild, moderate, severe, or okay, cases looks like, and we may want to use the ICD tree structure as a basis. For example, irritable inflammatory bowel condition will include underneath it Crohn's disease and UC, which means we have a different structure here. So you need to have the structure there because the structure indicates where it goes in some cases, if something says it says inflammatory bowel disease, it whatever they find may apply to Crohn's or UC or some other conditions which are underneath it. And the city may not provide coverage which one it applies to, or if it applies to several of them. If we have the details, we put it in details. If we don't, we put it on under the thing. So we end up having multiple hierarchies. We have to match the best match. And if the study indicates a member of the hierarchy, for example, it indicates honey, and then it talks about using a particular type of honey, then it becomes subjective. So do you have honey and the type of honey, or do you just have the type of honey? I'm inclined, if it mentions honey without qualification, you put honey there, and you put the qualified honey. Now that I got you saying, scream, you understand the issue of correct identification of the data in the article, and it is an interesting challenge. A lot of it can be automated, but whenever you automatically add something, you need to go back and have a mounting. You can get a high amount of things automatically populated using AI. Basically, this is stuff which you discover by inspecting the articles. Things that the AI may not necessarily be aware of or bother enumerating it. And when you add it automatically by inspection, you want to flag it for manual inspection. You put it in a hierarchical tree where it seems to be, and then you flag it later with its own unique ID. And if there's a change later, you can just go and move it in the hierarchical tree to wherever you want to be, keep the same ID, and the data that has been entered is still correct because the data is connected to the ID and not to a hierarchical structure, hopefully. So don't make your IDs for conditions and modifier hierarchical. Keep them as unique identifier so you can do a reorganization later without breaking the associations you have found. Verbs, adverbs, phrases, and all the glorious parts of the English language, which is needed to understand your sentence. Sometimes you may need to do a separate parsing. For example, if you're trying to identify if it has a probability associated with it, and regex can often be good to apply to a sentence to see if it's a probability is there, which is good, and deal with it that way. Things like terms associated and other non-directional terms generally have to be ignored. Hopefully, when you see the word associated, it does identify more, and there is an Excel spreadsheet associated, then you should flag that as double check this Excel spreadsheet or other data associated because it may indicate the direction there. Increases and decreases can have a variety of alternative variations. Some may be a little bit reduced. For example, diminish, enhance, grow, abundance. There's a whole bunch of different words that could be used. You want to have a appropriate thesaurus done of those terms, and those thesaurus terms probably will have additional ones added as you go through and do your manual creating of new terms. Again, when new terms are automatically added, you want to always flag them for manual review. Other terms can be a bit more challenging to do. For example, contextual terms such as what's the size of the population, how many different subsets is it? It's just comparing people with Crohn's disease to people with UC, in which case you're doing relative things and you may have to actually add into your database those qualifications. So, in other words, it's not just um, um, colostrum increases bifidobacterium for Crohn's disease and decreases it for, or has no, or decreases it for UC. You may have to add additional qualification into your statement of what the logical finding is. So be aware that it may not be A verb B, it may be A qualified verb B qualified, and the qualification can get slightly confused. When you do the processing, whether or not you make use of the qualifiers depends on the logic you decide to implement. And, for example, what creature was used instead of human, mice, dogs, pigs? Was this done on in a lab, so there was no actual creature done. You went and add time oil to a culture of E. coli and you see it disappear, or a probiotic, antibiotic, and it disappears. Again, all of those are a significant part of data harvesting, and those will or could be challenges for parsing the sentence apart. Manual training is very likely, to put it mildly. In fact, the first part you are spending lots of hours doing manual training. It's unlikely that the degree of accuracy we want will happen when the CAN package off the shelves. You've got some training to do. Applications should be designed to allow rapid addition. A new word identified, you should be able to add it in with a single click, or maybe a couple of clicks in the thing, and then goes to the database for qualification for later review by ideally a different party. Some keywords and phrases may appear that may be able to exclude the entire paper. For example, drinking water, plant pathogen, sausage, larva, sewage, pesticide are probably studies which have a very, very low risk of being significant, in which case you may want to just exclude them to begin with and save the parsing time to take the stuff apart. So that is basically it. That describes the process that needs to be done. I've implemented it. My method of implementing it, not everybody will agree with, and I have certain philosophy in there, and a lot of time I'm expecting things and saying, no, nothing is there, significant. Other time, yes, this is significant, and I'm doing on the fly. It's not fully automated. It is filtering things to a small subset. Typically, from 1,000 potential studies identified by bacteria name, my first run of processing will often reduce it to 300. Second type of automated filtering will reduce it to 50. And now I have 50 studies to manually review, of which 5 or 4, sometimes 1, is significant. And that's 50 studies I have to manually read, or the extractions. I'm working generally with the summaries from PubMed, not the full articles, simply to get the richest data set for the lowest possible cost. So that's something which you have to figure out. Are you going to be a full text shop? Are you going to be a summary shop? Are you how many studies are how many sources of things you're going to use? How strict are you going to be for what you deem to be a valid study to put in your database? There are a ton of different decisions which are to be done by you, and that is your decision or your management decision as to where you define things to be there. The bottom thing is a very distinct, unique data set from what and once you think you're ready, I can provide free of charge, provided I get reciprocity for access to your database findings, a list of full text PubMed articles which are good candidates to do your training on. Again, there's reciprocity requirement. You make use of this, and I expect to be able to access your findings so I can improve the quality of my own papers. I have a bunch of other papers which are not included. Doesn't matter to me. I just want to have as much good quality data as I can. So with that, I sign off. You got some learning to do, depending on what language you're wanting to use. You got a whole bunch of packages to get familiar with. You may well want to be running a battery of computers to do the processing because there's a lot of processing to be done. I don't suggest using Amazon Web Services or Google Cloud Services unless you got a very rich budget, because generally I find buying secondhand, fully refurbished PC will give you the power to do it, and then you're only paying for it for your domestic electricity costs, and you get better output than using the full thing. You may get a very warm room from all of the PCs, but that's livable. Okay, and that I will finish.